This is CS50, and this is both the start and the end, like literally almost the end of week 6. I thought I'd share a little bit of a fun fact. I pulled this up from a past semester's data set. You might recall that we ask you on every PSED form if you've watched online or if you've attended in person. And here is the data. So today was very much predictable, but we wanted to spend a bit of time with you nonetheless. Would anyone like to conjecture why this graph is so jaggy, up, down, so consistently? What do each of the peaks and troughs represent? Indeed. And more amusingly, God forbid we hold one lecture on a Friday at the beginning of the semester. That's what we see happen. So today we partake in a bit more about data structures, and to give you more of a solid mental model for problem set 5, which is now out, misspellings, wherein we'll hand you a text file of some 100,000 plus English words, and you're going to have to figure out how to cleverly load them into memory, into RAM, using some data structure of your choice. Now, one such data structure could be, but probably shouldn't be, the fairly simplistic linked list, which we introduced last time, and a linked list had at least one advantage over an array. What's one advantage of a linked list, arguably? Insertion, what do you mean by that?
Anywhere along the list, it's very easy to insert.
Good. So you can insert an element wherever you want in the middle of the list without having to shuffle anything, which we concluded in our sorting discussions isn't necessarily a good thing because it takes time to actually move all of those humans left or right. And so with a linked list, you can just allocate with malloc a new node and then update a couple of pointers, 2, 3 operations max, and we were able to slot someone in anywhere into a list. What else was advantageous about a linked list? Yeah. Perfect. Perfect. It's really dynamic in that you're not committing in advance to some fixed size chunk of memory like you would have to with an array, the upside of which is that you can allocate nodes only on demand, thereby using only as much space as you actually need. By contrast with an array, you might accidentally allocate too little, and then it's just going to be a pain in the neck to reallocate a new bigger array, copy everything over, free the old array, and then move about your business. Or worse, you might allocate way more memory than you actually need, and so you're going to have a very sparsely populated array, so to speak. So a linked list gives you these advantages of dynamism and flexibility with insertions and deletions, but surely there must be a price paid. In fact, one of the themes explored on Quiz Zero was a couple of the trade-offs we've seen thus far. So what's a price paid or a downside of a linked list? Yeah? No random access. But who cares? Random access doesn't sound compelling. Exactly. If you want to have a certain algorithm, and let me actually propose binary search in particular, which is one we've used quite a bit, if you don't have random access, you can't do that simple arithmetic of finding like the middle element and jumping right to it. You instead have to start at the first element and linearly search from left to right if you want to find the middle or any other element.
It also takes more memory.
Takes more memory. Where is that additional cost coming from in memory?
You have to hold both the integer value if it's an integer list and then the pointer to the list.
Exactly. In this case here, we had a linked list for integers, and yet we're doubling the amount of memory we need by also storing these pointers. Now, less of a big deal as your structs get larger, and you're storing not a number, but maybe a student or some other object, but the point certainly remains. And so a number of the operations on linked lists, recall, were big O of n, linear, things like insertion or search or deletion in case an element happened to be at the very end of the list, whether it's sorted or not. Sometimes you might get lucky, and so a lower bound on these operations might also be constant time if you're always looking at the first element, for instance. But ultimately, we promised to achieve the holy grail of data structures, or some approximation thereof, by way of constant time. Can we find elements or add elements or remove elements from a list? We shall see quite soon. And it turns out that one of the mechanisms we're going to start to use today, and you'll use in PSET 5, is actually pretty familiar. For instance, if this is a bunch of exam books, each of which has a student's first name and last name on it, and I pick them up from at the end of an exam, and they're all pretty much in a random order, and we want to go about sorting these exams so that once graded, it's just a lot easier and faster to hand them back out to students alphabetically. What would your instincts be for a pile of exams like this? Well, if you're like me, you might see that this is M, so I'm going to sort of put this into, if this is my table or my floor where I'm spreading things out, or my array, really, I might put all of the M's in there. Oh, here's an A, so I might put the A's over here. Oh, here's another A. I'm going to put that over here. Here's a Z. Here's another M. And so I might start making piles like this. And then maybe I'd go in later and sort of very nitpickily sort the individual piles. But the point is, I would look at the input that I'm handed, and I would make some calculated decision based on that input. If it starts with A, put it over there. If it starts with Z, put it over there, and everything in between. So this is a technique that's generally known as hashing, H-A-S-H, which generally means taking as input and using that input to compute a value, generally a number, and that number is the index into a storage container, like an array. So in other words, I might have a hash function, as I do in my head, that if I see someone's name who starts with A, I'm going to map that to 0 in my head. And if I see someone with Z, I'm going to map that to 25 in my head, and then put that into the lastmost pile. Now, if you think about not my brain, but a C program, what numbers could you rely on to achieve that same result? In other words, if you had the ASCII character A, how do you determine what bucket to put it in? You probably don't want to put it into bucket 65, which would be like over there for no good reason. Where do you want to put A in terms of its ASCII value? What do you want to do to its ASCII value to come up with a smarter bucket to put it in? Yeah, so minus A, or minus specifically 65 if it's a capital A, or 98 if it's a lowercase a. And so that would allow us to very simply and very arithmetically put something into a bucket like that. So it turns out we actually do this as well even with the quizzes. So you might recall you circled your teaching fellow's name on the cover, and the TF's names were organized into these columns alphabetically. Well, believe it or not, when all 80 plus of us got together the other night to grade, the last step in our grading process is to hash the quizzes into a big space of floor at the SOC and to lay everyone's quizzes out in exactly the order of their TF's names on the cover, because then it's a lot easier for us to search through that using linear search or some kind of cleverness for a TF to find his or her students' quizzes. So this idea of hashing that you'll see is quite powerful is actually pretty commonplace and very intuitive, much like perhaps divide and conquer was in week 0. Fast forward to the hackathon a couple of years ago. This was Zamila and a couple of other staff greeting students as they came in, and we had a whole bunch of folding tables there with name tags, and we had the name tags organized with like the A's over there and the Z's over there. And so one of the TFs very cleverly wrote this as the instructions for the day. And in week 12 of the semester, this all made perfect sense, and everyone knew what to do. But anytime you've queued in the same way, you're implementing the same notion of a hash. So let's formalize it a little bit. Here is an array. It's drawn to be a little wide just to depict visually that we might put strings in something like this. And this array is clearly of size 26 total, and the thing is called table arbitrarily, but this is just an artist's rendition of what a hash table might be. So a hash table now is going to be a higher level data structure. At the end of the day, we're about to see that you can implement a hash table, which is much like the check-in line at a hackathon, much like this table used for sorting exam books. But a hash table is sort of this high-level concept that could use an array underneath the hood to implement it, or it could use a linked list, or even perhaps some other data structures. And now that's the theme, taking some of these fundamental ingredients, like an array, and this building block now of a linked list, and seeing what else we can build on top of those, like ingredients into a recipe, making more and more interesting and useful final results. So with a hash table, we might implement it in memory pictorially like this, but how might it actually be coded up? Well, maybe as simply as this. If capacity, in all caps, is just some constant, for instance, 26 for 26 letters of the alphabet, I might call my variable table, and I might claim that I'm going to put char stars in there, or strings. So it's as simple as this if you want to implement a hash table. And yet this is really just an array, but again, a hash table is now what we'll call an abstract data type that's just sort of a conceptual layering on top of something more mundane now, like an array. Now, how do we go about solving problems? Well, earlier, I had the luxury of having enough table space here so that I could put the quizzes anywhere I wanted. So A's might go here, Z's might go here, M's might go here, and then I had some extra space. But this is a bit of a cheat right now, because this table, if I really thought of it as an array, is just going to be of some fixed size. So technically, if I pull up another student's quiz and see, oh, this person's name starts with an A2, I kind of want to put it there. But as soon as I put it there, if this table indeed represents an array, I'm going to be overwriting or clobbering whoever this student's quiz is, right? If this is an array, only one thing can go in each of these cells or elements, and so I kind of have to pick and choose. Now, earlier I kind of cheated and did this, or I just kind of stacked them above each other, but that's not going to fly in code. So where could I put the second student whose name is A if all I have is this available table space, and I've used 3 slots, and it looks like there's just a few others? What could you do? Yeah, maybe let's just keep it simple, right? It doesn't fit where I want to put it, so I'm going to put it technically where a B would go. Now, of course, I'm starting to paint myself into a corner. If I get to a student whose name is actually B, now B is going to be moved a little forward, as might happen, yep, if this is a B, now it has to go here. And so this very quickly could become problematic, but it's a technique that actually is referred to as linear probing, whereby you just consider your array to be along a line, and you just kind of probe or inspect each available element looking for an available spot. And as soon as you find one, you drop it in there. Now, the price being paid now for this solution is what? We have a fixed size array, and when I insert names into it, at least initially, what's the running time of insertion for putting the students' quizzes in the right buckets? Big O of what? I heard big O of n. Not true, but we'll tease apart why in just a moment. What else might it be? And let me do it visually. So suppose this is the letter S. It's 1. Right? This is an array, which means we have random access. And if we think of this as 0 and this is 25, and we realize that, oh, here's my input S, I can certainly convert S, an ASCII character, to a corresponding number between 0 and 25, and then immediately put it where it belongs. But of course, as soon as I get to the second person whose name is A, or B, or C eventually, if I've used linear probing as my solution, the running time of insertion in the worst case is actually going to devolve into what? And I did hear it here correctly early on. So it is n indeed once you have a sufficiently large data set. So on the one hand, if your array is big enough and your data is sparse enough, you get this beautiful constant time. But as soon as you start getting more and more elements, and just statistically you get more people with the letter A as their name or the letter B, it could potentially devolve into something more linear. So not quite perfect. So could we do better? Well, what was our solution before when we wanted to have more dynamism than something like an array allowed? What did we introduce? Yeah, so a linked list. Well, let's see what a linked list might do for us instead. Well, let me propose that we draw the picture as follows. Now, this is a different picture from an example from a different text, actually, that is actually using an array of size 31. And this author simply decided to hash strings, not based on the person's names, but based on their birth dates. Irrespective of the month, they figured if you're born on the 1st of a month or the 31st of a month, the author will hash based on that value so as to spread the names out a bit more than just 26 spots might allow. And perhaps it's a little more uniform than going with alphabetical letters, because of course there's probably more people in the world with names that start with A than certainly some other letters of the alphabet. So maybe this is a little more uniform, assuming a uniform distribution of babies across a month. But of course this is still imperfect, right? We're having collisions. Multiple people in this data structure are still having the same birth date, at least irrespective of month. But what has the author done? Well, it looks like we have an array on the left-hand side drawn vertically, but that's just artist's rendition. Doesn't matter what direction you draw an array, it's still an array. What is this an array of, apparently? Yeah, it looks like it's an array of linked lists. So again, to this point of sort of using these data structures now as ingredients to more interesting solutions, you can absolutely take a fundamental like an array, and then take something more interesting like a linked list, and even combine them into an even more interesting data structure. And indeed, this too would be called a hash table, whereby the array is really the hash table, but that hash table has chains, so to speak, that can grow or shrink based on the number of elements you want to insert. Now, accordingly, what's the running time now? If I want to insert someone whose birth date is October 31st, where does he or she go? Right, the very bottom, where it says 31, and that's perfect. That was constant time. But what if we find someone else whose birthday is let's see, October, November, December 31st. Where is he or she going to go? Same thing. 2 steps, though. That's constant, though, isn't it? Right, at the moment it is. But in the general case, the more people we add, probabilistically, we're going to get more and more collisions. Now, this is a little better, right? Because technically now, my chains could be, in the worst case, how long? If I insert n people into this more sophisticated data structure, n people, in the worst case, it's going to be n. Why?
Because if everyone has the same birthday, they're going to be in one line.
Perfect. It might be a little contrived, but truly in the worst case, if everyone has the same birthday, given the inputs you have, you're going to have a massively long chain. And so you can call it a hash table, but really it's just a massive linked list with a whole lot of wasted space. But in general, if we assume that at least birthdays are uniform, and it probably isn't, I'm making that up, but if we assume for the sake of discussion that they are, then in theory, if this is the vertical representation of the array, well then hopefully you're going to get chains that are, roughly the same length, where each of these represents a day of the month. Now, if there's 31 days in the month, that means my running time really is big O of n over 31, which feels better than linear. But what was one of our commitments a couple weeks ago whenever we came to expressing the running time of an algorithm? Just only look at the high order term, right? 31 is definitely helpful, but this is still big O of n. But one of the themes of problem set 5 is going to be to acknowledge that absolutely, asymptotically, theoretically, this data structure is no better than just one massive linked list. And indeed, in the worst case, this hash table might devolve into that. But in the real world, with us humans that own Macs or PCs or whatever, and are running real world software on real world data, which algorithm are you going to prefer? The one that takes n steps, or the one that takes n divided by 31 steps to find some piece of data or to look up some information? I mean, absolutely, the 31 makes a difference in the real world. It is 31 times faster, and we humans are certainly going to appreciate that. So realize the dichotomy there between actually talking about things theoretically and asymptotically, which definitely has value, as we've seen. But in the real world, if you care about just making the human happy for general inputs, you might very well want to accept the fact that, yes, this is linear, but it's 31 times faster than linear might be. And better yet, we don't just have to use something arbitrary like a birth date. We could spend a little more time and cleverness and think about what we might do, given a person's name and maybe their birthday, to combine those ingredients to figure out something that is truly more uniform and less jaggy, so to speak, than this picture currently suggests it might be. How could we implement this in code? Well, let me propose that we just borrow some syntax we've used a couple times thus far, and I'm going to define a node, which again is a generic term for just some container for some data structure. I'm going to propose that a string is going in there, but we're going to start taking those training wheels off now. No more CS50 library, really, unless you want to use it for your final project, which is fine. But now we're going to pull back the curtain and say it's just a char star. So the word there is going to be the person's name in question. And now I have a link here to the next node so that these represent each of the nodes in the chain, potentially, of a linked list. And now how do I declare the hash table itself? How do I declare this whole structure? Well, really, much like I used a pointer to just the first element of a list before, similarly, can I just say I just need a bunch of pointers to implement this whole hash table? I'm going to have an array called table for hash table. It's going to be of size capacity. That's how many elements can fit in it. And each of those elements in this array is going to be a node star. Why? Well, per this picture, what I'm implementing the hash table as effectively in the beginning is just this array that we've drawn vertically, each of whose squares represents a pointer. The ones that have slashes through them are just null, and the ones that have arrows going to the right are actual pointers to actual nodes, ergo the start of a linked list. So here then is how we might implement a hash table that implements separate chaining. Now, can we do better? Right, I promised last time that we could achieve constant time, and I kind of gave you constant time here, but then said, not really constant time, right? Because it's still dependent on the total number of elements you're inputting into the data structure. But suppose we did this. Let me go back to the screen over here. Let me also project this up here. Clear the screen, and suppose I did this. Suppose I wanted to insert the name Davin into my data structure. So I want to insert a string Davin into the data structure. What if I don't use a hash table, but I use something that's more tree-like a family tree, where you have some root at the top and then nodes and leaves that go downward and outward? Suppose then that I want to insert Davin into what's currently an empty list. I'm going to do the following. I'm going to create a node in this family tree-like data structure that looks a little like this, each of which rectangles has, let's say 26, for now 26 elements in it. And each of the cells in this array is going to represent the letter of an alphabet. Specifically, I'm going to treat this as A, then B, then C, then D, this one here. So this is going to effectively represent the letter D. But to insert all of Davin's name, I need to do a bit more. So I'm first going to hash, so to speak. I'm going to look at the first letter in Davin's name, which is obviously a D, and I'm going to allocate a node that looks like this, a big rectangle big enough to fit the whole alphabet. Now, OK, D is done. Now A, D-A-V-E-N is the goal. So now what I'm going to do is this. As soon as I start at D, notice there's no pointer there. It's garbage values at the moment, or I might initialize it to null. But let me keep going with this idea of building a tree. Let me allocate another one of these nodes that has 26 elements in it. And you know what? If this is just a node in memory that I created with malloc using a struct, as we'll soon see, I'm going to do this. I'm going to draw an arrow from the thing that represented D down to this new node. And now, for the next letter in Davin's name, V, D-A-V, I'm going to go ahead and draw another node like this, whereby the V element here, which we'll draw, for instance, whoops, we won't draw there, is going to go here. Then we're going to consider this to be V. And then down here, we're going to index down from V into what we'll consider E. And then from here, we're going to go have one of these nodes here. And now we have a question to answer. I need to somehow indicate that we're at the end of the string Davin. So I could just leave it null. But what if we have Davin's full name also, which is, as we've said, Davenport? So what if Davin is actually a substring, a prefix of a much longer string? We can't just permanently say nothing is going to go there, because we could never insert a word like Davenport into this data structure. So what we could do instead is treat each of these elements as, maybe having two elements inside of them. One is a pointer, indeed, as I've been doing. So each of these boxes is not just one cell. But what if the top one, the bottom one's going to be null, because there is no Davenport just yet. What if the top one is some special value? And it's going to be a little hard to draw at this size. But suppose it's just a check mark. Check, D-A-V-E-N, is a string in this data structure. Meanwhile, if I had more space here, I could do P-O-R-T, and I could put check in the node that has the letter T at the very end. So this is a massively complex-looking data structure, and my handwriting certainly doesn't help. But if I wanted to insert something else, consider what we would do. If we wanted to put David in, we'd follow the same logic, D-A-V. But now I would point in the next element not from E, but from I to D. So there's going to be more nodes in this tree. I'm going to have to call malloc more, but I don't want to make a complete mess of this picture. So let's instead look at one that's been pre-formulated like this, with not dot, dot, dots, but just abbreviated arrays. But each of the nodes in this tree up here represents the same thing, an array of size 26. Or if we want to be really proper now, what if someone's name has like an apostrophe? Let's assume that each node actually has like 27 indexes in it, not just 26. So this now is going to be a data structure called a trie, T-R-I-E. A trie, which is supposedly historically a clever name for a tree that's optimized for retrieval, which of course is spelled with an I-E, so it's trie. But that is the history of the trie. So a trie is this tree-like data structure, like a family tree, that ultimately behaves like that. And here is just another example with a whole bunch of other people's names. But the question now at hand is, what have we gained by introducing arguably a more complicated data structure, and one, frankly, that uses a lot of memory? Because even though at the moment I'm only using D's pointer and A and V and N and E's and N's, I'm wasting a heck of a lot of memory. But where I spend one resource, I tend to gain back another. So if I'm spending more space, what's probably the hope? That I'm spending less what? Time. Now, why might that be? Well, what is the insertion time in terms of big O now of a name like Davin or Davenport or David? Well, Davin was 5 steps. Davenport would be 9 steps, so it would be a few more steps. David would be 5 steps as well. So those are concrete numbers. But surely there's an upper bound on the length of someone's name. And indeed, in the problem set 5 specification, we're going to propose that it's something that's 40 some odd characters. Realistically, no one has an infinitely long name, which is to say that the length of a name or the length of a string we might insert into this data structure is arguably what? It's constant, right? It might be a big constant, like 40 something, but it is constant, and it has no dependency on how many other names are in this data structure. In other words, if I wanted to now insert Colton or Gabriel or Rob or Zamila or Allison or Belinda or any other names from the staff into this data structure, is the running time of inserting other names going to be at all impacted by how many other elements are in this data structure already? It's not. right? Because we're effectively using this multi-layer hash table, and the running time of any of these operations is dependent not on the number of elements that are in the data structure or that are eventually going to be in the data structure, but on the length of what specifically? The string being inserted, which does make this asymptotically constant time, big O of 1. And frankly, just in the real world, this means inserting Davin's name takes like 5 steps, or Davenport 9 steps, or David 5 steps. That's pretty darn small running times, and indeed that's a very good thing, especially when it's not dependent on the total number of elements in there. So how might we implement this kind of structure in code? It's a little more complex, but still it's just an application of basic building blocks. I'm going to redefine a node as follows. Bool called word, and this could be called anything, but the bool represents what I drew as a check mark. Yes, this is the end of a string in this data structure. And of course, the node star there is referring to children. And indeed, just like a family tree, you would consider the nodes that are hanging off of the bottom of some parent element to be children. And so the children is going to be an array of 27, the 27th one just being for apostrophe. We're going to sort of special case that, so you can have certain names with apostrophes. Maybe even hyphens should go in there. But you'll see in PSET 5, we only care about letters and apostrophes. And then how do you represent the data structure itself? How do you represent the root of this trie, so to speak? Well, just like with a linked list, you need a pointer to the first element. With a trie, you just need one pointer to the root of this trie. And from there, you can hash your way down deeper and deeper to every other node in the structure. So simply with this, can we represent that struct? Now, meanwhile, question. Bool word is just the C incarnation of what I described in this box here. When I started splitting each of the array's elements into 2 pieces, one is a pointer to the next node. The other has to be something like a checkbox to say, yes, there's a word Davin that ends here, because we don't want, at the moment, Dave. Even though Dave is going to be a legitimate word, he's not in the trie yet. And D is not a word, and DA is not a word or a name. So the check mark indicates only once you hit this node is the previous path of characters actually a string that you've inserted. So that's all the bool there is doing for us. Any other questions on tries? Yeah?
What if they overlap? What if we have a Dave and a Davin?
Perfect. What if you have a Dave and a Davin? So if we insert, say, a nickname for David, Dave, D-A-V-E, this is actually super simple. It's only going to take 4 steps, D-A-V-E. And what do I have to do once I hit that 4th node? Just going to check. We're already good to go. Done. 4 steps, constant time asymptotically. And now we've indicated that both Dave and Davin are strings in this structure. So not a problem. And notice how the presence of Davin did not make it take any more time or less time for Dave, and vice versa. So what else can we now do? We've used this metaphor before of trays representing something, but it turns out that a stack of trays is actually demonstrative of another abstract data type, a higher level data structure that at the end of the day is just like an array or a linked list or something more mundane, but it's a more interesting conceptual concept. A stack, like these trays here in Mather, are generally called just that, a stack. And in this type of data structure, you have 2 operations. You have one called push, for adding something to the stack, like putting another tray back on the top of the stack, and then pop, which means you take the topmost tray off. But what's key about a stack is that it's got this curious characteristic. As the dining hall staff are rearranging the trays for the next meal, what's going to be true about how students interact with this data structure? They're going to pop one off, hopefully the top, otherwise it's just kind of stupid to go all the way to the bottom, right? The data structure doesn't really allow you to grab the bottom tray, at least easily. So there's this curious property to a stack that the last item in is going to be the first one out. And computer scientists call this LIFO, last in, first out. And it actually does have interesting applications. It's not necessarily as obvious as some others, but it can indeed be useful, and it can indeed be implemented in a couple of different ways. So one, and actually, let me not dive into that. Let's do this instead. Let's look at one that's almost the same idea, but it's a little fairer, right? If you're one of these fanboys or girls that really likes Apple products and you woke up at 3 a.m. to line up at some store to get the very latest iPhone, you might have queued up like this. Now, a queue is very deliberately named. It's a line. because there's some fairness to it, right? It would kind of suck if you got there first at the Apple store, but you're effectively the bottommost tray because the Apple employees then pop the last person who actually got in line. So stacks and queues, even though functionally they're kind of the same, it's just this collection of resources that's going to grow and shrink, there's this fairness aspect to it, at least in the real world, where the operations you exercise are fundamentally different. A queue rather, is said to have two operations, enqueue and dequeue. Or you can call them any number of things, but you just want to capture the notion that one is adding and one is ultimately subtracting. Now, underneath the hood, both a stack and a queue could be implemented how? We won't go into the code of it because the higher level idea is sort of more obvious. I mean, what do humans do? If I'm the first person at the Apple store and this is the front door, I'm going to stand here, and the next person's going to stand here, and the next person's going to stand here. So what data structure lends itself to a queue? Well, a queue, sure. What else? A linked list. You could implement it. And linked list is nice because then it can grow arbitrarily long as opposed to having some fixed number of people in the store. But maybe a fixed number of places is legitimate because if they only have like 20 iPhones on the first day, maybe they only need an array of size 20 to represent that queue. Which is only to say, now once we start talking about these higher level problems, you can implement it in any number of ways. And there's probably just going to be a trade-off in space, in time, or just in your own code complexity. What about a stack? Well, a stack we've seen too can just be these trays, and you could implement this in an array. But at some point, if you use an array, what's going to happen to the trays you're trying to put down? Right? You're only going to be able to go so high. And I think in Mather, they're actually recessed in that opening. So indeed, it's almost like Mather is using an array of fixed size because you can only fit so many trays in that opening in the wall down below people's knees. And so that might be said to be an array, but we could certainly implement that more generally with a linked list. Well, what about another data structure? Let me pull up one other visual here. Something like, how about this one here? Why might it be useful to have not something as fancy as a trie, which we saw had these very wide nodes, each of which is an array, but what if we do something more simply, like an old school family tree, each of whose nodes here is just storing a number. Instead of a name or a descendant, it's just storing a number like this. Well, the jargon we use in data structures, both tries and trees, where a trie, again, is just one whose nodes are arrays, is still what you might use from grade school when you made a family tree. Leaves and the root of the tree and children of the parent and siblings thereof. And we might implement a tree, for instance, as simply as, this. A tree, if it has a node, one of these circles that has a number, it's not going to have one pointer, but two. And as soon as you add a second pointer, you can actually now make sort of two-dimensional data structures in memory. Much like a two-dimensional array, you can have kind of two-dimensional linked lists, but ones that follow a pattern where there's no cycles. It's truly a tree with one grandparent way up here, and then some parents and children and grandchildren and great-grandchildren and so forth. But what's really neat about this, too, just to tease you with a bit of code, recall recursion from a while back, whereby you write a function that calls itself. This is a beautiful opportunity to implement something like recursion, because consider this. This is a tree, and I've been a little anal with how I've put the integers into this tree, so much so that it has a special name, a binary search tree. Now, we've heard of binary search, but can you work backwards from this thing's name? What is the pattern of how I inserted the integers into this tree? It's not arbitrary. There's some pattern, yeah. Yeah, smaller ones are on the left, bigger ones are on the right, such that a true statement is a parent is greater than its left child, but less than its right child. And that alone is even a recursive verbal definition, because you can apply that same logic to every node, and it only bottoms out, a base case, if you will, when you hit one of the leaves, so to speak, where a leaf has no children further. Now, how might you find the number 44? You would start at the root and say, 55 is not 44, so I want to go right or I want to go left? Well, obviously you want to go left. And so it's just like the phone book example and binary search more generally, but we're implementing it now a little more dynamically than an array might allow. And in fact, if you want to look at the code, at first glance, sure, it looks like a whole bunch of lines, but it's beautifully simple. If you wanted to implement a function called search, whose purpose in life is to search for a value like n, an integer, and you're passed in one pointer, a pointer to the node of the root rather of that tree, from which you can access everything else. Notice how straightforwardly you can implement the logic. If tree is null, obviously it's not there. Let's just return false, right? If you handed nothing, there's nothing there. else if n is less than tree arrow n. Now, arrow n, recall we introduced super briefly the other day, and that just means dereference the pointer and look at the field called n. So it means go there and look at the field called n. So if n, the value you're given, is less than the value in the tree's integer, where do you want to go? To the left. So notice the recursion. I'm returning, not true, not false. I'm returning whatever the answer is from a call to myself, passing in n again, which is redundant, but what's slightly different now? How am I making the problem smaller? I'm passing in as the second argument, not the root of the tree, but the left child in this case. So I'm passing in the left child. Meanwhile, if n is bigger than the node I'm currently looking at, I search the right-hand side. Else, if the tree is not null, and if the element's not to the left and it's not to the right, what is wonderfully the case? We've actually found the node in question, and so we return true. So we've just scratched the surface now of some of these data structures. In problem set 5, you'll explore these yet further, and you'll be given your design choice of how to go about this. What I'd like to conclude on is just a 30-second teaser of what awaits next week and beyond. As we begin, thankfully, you might think, our transition slowly from the world of C and lower-level implementation details to a world in which we can take for granted that someone else has finally implemented these data structures for us, and we'll start to understand the real-world means of implementing web-based programs and websites more generally, and also the various security implications that we've only begun to scratch the surface of. Here is what awaits us in the days to come.
He came with a message, with a protocol all his own. To a world of cruel firewalls, uncaring routers, and dangers far worse than death. He's fast, he's strong, he's TCP/IP, and he's got your address. Warriors of the Net.
Coming next week. We will see you then.
And now, Deep Thoughts by Davin Farnham.
David always starts lectures with, "All right." Why not, "Here's the solution to this week's problem set," or "We're giving all of you an A."